What's up, everybody? Welcome back. We're going to be working through some more fluid mechanics problems today. Today's really exciting. We're going to get into Bernoulli's equation, and we're going to do that through some energy balance applications. After that, we'll move on to two practice type questions where we get to apply Bernoulli's equations both to temperature change and flow situations. Keep in mind during today's video, and I'll mention this a few times throughout, all of the applications we're going to be using Bernoulli's equation with today are for non-viscous fluids. So the applications you'll see today, and I'll explain it when we get there, are for no viscosity situations. All right, so with that, let's jump right into number one. We've got four sections to work through today. And number one is the derivation. Derive and explain an energy balance for flow systems. And then from that, we'll move into number two, which is we're going to find Bernoulli's equation from that energy balance equation. So let's talk about energy. So for a flow system, so what that means, we're interested in some sort of system like a pipe with fluid flowing through it. I guess presumably left to right or something like that, right? And so we need to think about the energy equation for this. There's going to be multiple types of energy that go into a system like this and multiple types that come out. And we're going to set up an equation for all of this. So presumably in this situation, there's flow, which means there has to be some sort of thing initiating or triggering the flow. It could be a number of things. It could be caused by, say, a change in height, right? Like some force due to gravity moves a fluid down. It could be due to a change of pressure. It could be due to a lot of different things, and we got to encapsulate all of those things into our equation. The first thing we're going to work with is let's put pressure and work into our equation first. So let's think about this. We've got a pipe here, and on one side of the pipe, we have a pressure. We'll call it pressure 1. And on the other side of the pipe, we have another pressure. We'll call it pressure 2. And presumably, pressure 2 is lower than pressure 1 since the flow is traveling in this direction and there's no noticeable, height changes that we can see in my picture I drew. But let's just say for now, pressure 1 is bigger than pressure 2. And with that, we have some volume going in to the pipe at one end, right? And some volume coming out of the pipe at the other end. And simple logic would tell us what comes in must go out some fashion, right? And so we have this pressure that causes a force across this area, which pushes a volume of fluid in, and the same thing happens out the other side. Okay, so let's think about this situation right here. We have some force being applied in, and it's moving some small amount of fluid, some small amount of mass, a certain distance. And honestly, we know our definition, our most simple definition of work here is force times distance. Okay? So how can we relate this simple equation? How can we take this simple equation and use things that are actually applicable to us in a flow system like pressure and volume? Well, we know that force is related to pressure, right? So pressure is force over area, right? So our force is simply equal to a pressure times an area. Right, where our area is like this cross-sectional area that the force due to a pressure is being applied at. Okay, and what about this distance here? Well, we can relate the distance to the volume. If we say this is our volume, right, of fluid that's being pushed in here, that volume is simply equal to the cross-sectional area times the distance. So distance we could rewrite this, it's a little silly, but distance is volume over area. Okay, so we plug this all back in, we get work equals the pressure times the area times the volume over the area. And you'll see that our areas cancel out. And this is actually where we get the alternate definition of work. Work equals P times V. Okay, but what good is that? Maybe we only know the type of fluid in the system. So we can take our volume here, and we know what volume is as a function of mass and density. Okay, and that's where this gets really important. So our volume, well, let's start this way. Density is equal to mass over volume, right? So we can substitute this here. Pressure times mass over density. And this is going to be really important because as we talk about energy in a flow system, all these energies are going to be related through one common variable, and that's mass. So what we're going to end up doing is talking about each of these energies in the system in terms of mass, so per mass. So if we look at work per mass, we get that is equal to pressure over density. Okay, and this is what we're going to use here in our energy balance equation, for work at least. Okay, and so our work per unit mass is equal to pressure over density. So what other energies exist inside this, inside a flow system? Not necessarily this one, but inside a flow system. Well, we have, say for example, we talked about a change in height. So that would be like a potential energy difference, right? We have potential energy. We know potential energy is mgh. And again, we see that mass here is in common. So if we talk about potential energy per unit mass, we get gh. There's also kinetic energy. So the fluid carries some kinetic energy because it's movement. Per unit mass, this is equal to 1/2 v squared, right? 1/2 mv squared divided by m. We might also have some internal energy. This is known usually as U. And we know U as mc delta T, but per unit mass, we have C delta T. What else do we have? Well, maybe we have energy added to the system through a direct source of heat. Okay, so maybe that's like, that would be Q, right? Some direct source of heat. Okay, and what else we can do? Oh, we can add like a non-flow work, right? So maybe we have like a stirrer in the middle or something like that that spins around and adds work to the system, but it's not flow related. So this work is flow related. It's due to the change in pressures and it's flow related work, but maybe we add work somewhere in the middle. That would be, we should just call it work non-flow, NF. Okay, so we have all of these energies that we now have to put into the system. And remember what we said at the beginning, what goes in must come out, and that's going to be the basis for us writing this equation. So we're going to do this, it's going to look a little weird, but in differential units of mass effectively, okay? So let's go ahead and start writing this. So we have, in this system, we have some amount of energy. We'll call this, at any specific point in the system, we have a differential amount of this energy. And in general, again, I'm factoring our mass out here. Our energy is equal to we have some potential energy, right? We have some kinetic energy. We have some internal energy, okay? And this is all equal to, what are we going to put on the other side of this equation? Well, we have the in and the out of each of these effectively, right? So let's start with these energies again. So there's some, we'll call potential energy, we'll call this look at H1, and we'll call, this will work. We'll do, let me think about how I want to do this. We'll do GH, let's keep them together just like we did on the other side. I think that'll be easier. Times some small amount of mass in, right? Minus the same thing that goes out. So we have GH2, maybe this is like velocity, hold on, E1. And you can see where this is going, right? We have in minus out. So the change in energy is equal to the change in energy. Makes sense. And then we said we might also have some flow related work, okay? So we have P1 over rho times Sn. Remember, that's work per mass. So I'm kind of adding it back in there. You'll see how it all comes together here in a minute. Right. And then we have the same thing, but out. Okay. And then maybe we add, what do we say? We said maybe we add some, what is that, heat? Some heat. Directly applied heat. So some small amount of heat. And then, who knows, maybe we add some work to a part of the system that's not related to flow. So call it dW. And then non-flow related. Okay. So that would describe the change in energy in the system. We're at some energy in, and maybe we add some more, and maybe we add some more, and the same thing comes out, right? And, well, maybe not the same thing, but something comes out, and that change in energy is equal to the change in energy of the system. So that works out. Now, let's simplify this a little bit, right? We have, how do we want to do this? I think this is simplified enough. So we're going to continue to simplify this equation as we work into number 2, because number 2 will give us some conditions on this equation. But in general, this is our energy balance equation. So I'm comfortable leaving this here, and then I'm going to erase what's above it so we can keep working into number 2. And number 2 says, assuming a steady state, adiabatic conditions, no change in internal energy, and no non-flow work derived Bernoulli's equation. I'm going to erase what's up here for us. Just so we have some more room. Okay. Let's see, is that where I want to leave it? I think so. Okay, so this is our answer to number 1 here. So, assuming steady state, adiabatic conditions, no change in internal energy, no non-flow work, derive Bernoulli's equation. So let's break this apart piece by piece in our question. So assuming a steady state, what does that mean? It means this has been happening for a long time, it's steadied out, meaning the change in energy of the system is equal to 0. Okay? And the reason it's equal to 0 is because this mass factors, the mass in and mass out are equal to 0. So mass in, sorry, not equal to 0, they're equal to each other. Mass out are equal to each other. Okay, so the change in this is 0. So that's what a steady state means. So let's go ahead and rewrite this, assuming a steady state. 0 equals, now if the mass in and the mass out are the same because it's a steady state, then dm in and dm out are the same. We can just call them m, right? So what this whole big expression is when we simplify, this is why I wanted to leave it here for part 1 and move on to part 2. What this really shows us is like, we can factor mass out of this, right? And then we can divide mass out, right? And right? And when we divide both sides by m, we get rid of them and then divide these by m. Okay? So that's really what we're left with once we simplify all this, assuming a steady state. Okay, so let's go ahead and rewrite that now. So these two terms, we have gh1 plus 1/2 v1 squared plus u1 minus gh2 plus 1/2 v2 squared. We can put all these terms together. We're going to get g times h1 minus h2 plus, what is this, v1 squared minus v2 squared over 2. Do that right? Plus, plus, plus. Oh, excuse me, that should be a minus. Okay, and then we get a u1 minus u2. Okay, and make sure I didn't miss that there. It's important, our parentheses are important. Okay, so we've taken care of the top. We get down to the bottom, we have, I'm gonna bracket this. Hold on a second. We might have had too many minus signs. I just want to double check this. So these should be plus signs. I confused myself looking at it. So we have gh1 minus gh2 plus 1/2 v1 squared plus 1/2 v2 squared. All right. Okay, so those are plus signs. Okay, we got that there. I knew something looked a little funky. Now, we have our work component due to our pressure. We have P1 minus P2 over rho. And the reason I don't have rho 1 and rho 2 is because I would hope that in this case the density remains constant of the fluid. We're going to assume that the density remains constant. So it's the same rho 1 equals rho 2. No need for numbers there. Okay, and then we have any heat we directly add to a point of the system per unit mass. This whole thing's in per unit mass. And then we have any non-flow related work per mass. Okay. So this is the steady state condition. We got that. This equals 0, and the mass coming in is equal to the mass coming out. Just calling it m. Just to recap, we have all of this now in per unit mass. That's why we have divided by dm, and there's no dm's in the rest of this. I'm gonna erase this to give us more room. Try to keep the answers on the board, but they're so long in this problem that we're just gonna have to keep moving. Okay, so we got the steady state. Now, adiabatic conditions, what does adiabatic mean? Adiabatic means Q equals 0, Okay, so this term, they're saying we're not adding any heat there. Adiabatic conditions, check. No change in internal energy of the fluid. That is U1 minus U2. Okay, and no non-flow work. This guy right here. Okay, so if we rearrange these around in our equation, we're going to get, let's go ahead and I did this a little bit out of order than maybe what we're used to, but I'm going to go ahead and put these to the other side of the equation. Okay, so we have G, and watch, I'm going to change the signs of all these, H2 minus H1. That effectively is, right, delta H, or what we think of as delta H. So we have G delta H plus, changing the signs, we have V2 squared minus V1 squared over 2. Okay, plus, we said that it's plus delta U here, but we said this is going to 0, okay? And for the sake of, no, what the heck, we're gonna keep it on that side, just for one more step. We have P1 minus P2 over rho, and then plus dQ dm, which we said was 0, plus dWf dm, which we also said was 0 for this problem. Okay, and really this is like the relationship that is Bernoulli's equation as it's most thought of. When we have a steady state adiabatic conditions, no change in internal energy, and no non-flow related work. We can make it look a little bit prettier if we put our work on one side and set the whole thing equal to 0. So now we have G delta H plus V2 squared minus V1 squared over 2. Putting this on the other side, we get plus, but I'm going to switch these, so we get delta P over rho equals 0. And that is Bernoulli's equation in this form, right? Steady state, adiabatic conditions, no change in internal energy, and no non-flow work. Now, the reason that this term, and this term are 0 is because we don't have a viscous fluid. We're not accounting for viscosity. So in later videos, we'll come back to viscosity. Maybe in a few videos, it's going to take us a few to get there. We'll come back to viscosity, and these terms will not always be 0. There's other reasons they might not be 0, but in general, no viscosity, we have 0 on the other side of the equation. And so we got the other side. Okay, so we've completed number 2. Let's go ahead and do some applications of this equation. I'm going to try to keep this up so that we can see this work and do number 3. So we have for a constant diameter pipe with no change in height, so kind of like this one right here, or heat flow, derive an expression for the change in temperature associated with a change in pressure of negative 60 psi. So that basically means we're dropping 60 psi across the flow of the pipe. I'm going to use the same picture, but just get rid of my stirrer I put in there. So maybe we have 60 psi over here and 0 over here. Okay, that's effectively what they're saying. We have a delta P of negative 60. And we want, what does it say? Derive an expression for the change in temperature. Okay. So, I'm going to rewrite, this is kind of our main equation here before we simplified it. We don't have the same conditions necessarily, but what we do know here is that, let's put this back together. So G delta H plus V2, 1, 2, plus delta, actually I'm going to put this back the other side, plus delta P over rho equals, I'm putting that delta U back on the other side, so we have U1 minus U2 plus dQ plus dW. Okay. So we've rearranged our equation. Let's look at our question again. So we know we're going to have some change in pressure, so we're going to keep this term, right? We don't have any change in height. No problems. That's equal to 0. We don't need to worry about that. We know that there's going to be some change in temperature. The question didn't state it, so we're going to assume that there's no change in these two either. Not adding any work or heat to the system, adiabatic. And no change in velocity either. The pipe is cylindrical, it's not constricting or widening at all. So, velocity will not change. Okay. We're just left with those two terms. That's pretty easy. Delta P over rho equals U1 minus U2. So we said delta P, if we drop 60 psi, that is a delta P of, it'd be like 0 minus 60, right? P2 minus P1, so negative 60. Okay, and we're going to assume this is water. I don't think I wrote it down, but in this scenario, we're going to call this water. The density of water is 1,000 kilograms per meter cubed. We'll take care of our units here in a second. So that's delta P over rho. And this is going to be equal to the change in internal energy there. So what did we say that little u was? So we have to remember back, little u there is basically like big U per unit mass, right? And so if big U is like, we said that was like mc delta T, little u is c delta T. Okay. So U1 minus U2, we gotta have C, I'm gonna factor the C out. C is constant, times temperature 1 minus temperature 2. Okay? Let's go ahead and get our pressure in better units. We have pounds per square inch here. We're gonna put that into pascals, so that we can make it work with our density. We have negative 60 psi times, there is, oh boy, 101.325 pascals per 14.7 psi. Does that sound right? I'll check that later. Divided by 1,000 equals, C is 4,186, and we'll just call this negative delta T. T2 minus T1. Joules per kilogram degrees. Yeah, so 4186 is in joules per kilogram degrees Celsius, I believe. Okay. Let's go ahead and plug that into the old calculator and see what we get for delta T. All right. So 60, negative 60 times 101.325 over 14.7 divided by 1,000 divided by 4186 gives us a change in temperature sounds about right. I get a change in temperature of 0.099 degrees C. Okay, so the temperature changes about 0.01 degrees from one end of the pipe to the other. It's interesting, right? Okay, so that's one application of Bernoulli's equation. That's going to be the answer to number 3. Okay, so I think we got number 3 taken care of. Just write that down, 0.01 degrees C about. I'm going to erase this, give us some more room so we can do another problem real quick, and then we'll be all done for this video. Okay, so given a tank containing fluid at a level of H with a hole of size A at the bottom, derive an expression for the volumetric flow rate out of the tank. Okay, let's go ahead and draw our tank. I'll just say it's sitting on the ground here. And there's some fluid in it, sounds like, with a hole at the bottom. So fluid's pouring out, right? Okay, it says given a fluid at a level of H, so I guess we're calling this H here. I guess that makes sense to call this 0, at where the hole is, right? And a hole of size A, so if this is our hole, the area of it is A. Derive an expression for the volumetric flow rate out of the tank. Okay, so what is flow rate? Flow rate is a volume pouring out of an area, right? So we call flow rate Q traditionally, and that equals V times A. So what we need here, well, we need V, right? That's it. We have A, and we're going to keep it in terms of A. We just need V. What is Q? Hang on, let's figure out these units real quick. So I want to double check this. So Q is flow rate, V and A. So we know A is in meters squared, and V. See, here's where I messed up. Good thing we checked. I said V was a volume. No, it's a velocity, right? It only makes sense if it's a velocity. Meters per second times meters squared. Q is the volume per time, right? It's a flow rate. We're looking for volume, which would be like meters cubed per second. And so then V has to be velocity if A is area, right? It'd be like saying velocity meters per seconds times meters squared. That makes sense. Okay, so V is velocity. Excuse me. I misspoke earlier, but that's why we check our units, right? So Q equals V times A. So we need V. We can get V from Bernoulli's equation. Good thing we just derived it. Let's go ahead. I'm gonna write that over here. Q equals VA. Let's go ahead and use our Bernoulli's equation again. Okay, so we have some change in height, right, as the water is dropping. Well, as water's flowing out, the water's dropping, so we have a change in height. We have, this is interesting, so change in velocity. Do we really have a change in velocity? Well, the velocity traveling out here, something, but I guess the velocity of the water dropping in the tank is probably so small, it's negligible, right? So I guess we could say, like, if this is V 2. This is V1, and V1 is just 0. The water's moving out quickly, of course, it's coming out of a small hole, but you know, the tank, I would imagine, is so large that V1 is negligible. We'll just call it 0. That only makes sense. Okay, and well, is there a change in pressure? Well, here, when it comes out, it's atmospheric pressure. If we're using a gauge pressure, we'd say 0, right? And at the surface of the water, the pressure is 0. If the pressure of the water was more than 0 when it came out, the water would just kind of spray out like this, right? But it's kind of just pouring out. So there's pressure behind it, obviously, but when it leaves, it's also 0. So really, there's no pressure component to this that we have to worry about. We're not adding work or heat to the system. And so I think that's really the only things we have to worry about is the change in height is going to change the energy of the system, right? Potential energy. There's going to be a change in kinetic energy because the water is barely moving, so small we can call it 0 when it's in the tank, but when it comes out of the tank, it has energy. So the system's losing energy when we let the water out. And I think that's it. So what we can do here is we can say that if all these other terms are 0, we just have G delta H plus V2 squared minus V1 squared over 2 equals 0. And we already said that V1 itself is 0. Okay, so let's just go ahead and solve this. We have G times change in height is 0 minus H. Okay, so that is going to be equal to, I'm going to move this to the other side, negative, we have V2 squared over 2. Obviously, we're going to get negative GH here. No reason to carry these negative signs around, so I'm just going to cancel negative sign, equals V2 squared over 2. Okay, and remember we're solving for velocity to plug into our flow rate formula. And we get 2GH is equal to V2, and of course we'll square root it to get rid of our square. Okay, that's pretty simple. So now we'll go Q equals, this is our expression for the velocity here. We get radical 2GH times the area of the hole. I think that's it. Given a tank containing fluid at a level of H with a hole of size A at the bottom, derive an expression for the volumetric flow rate out of the tank. We get volumetric flow rate here, and I think we're good to go. So thanks for bearing with me through that thought process. It takes a little bit of time to derive these equations, and I hope we got them all down here right. So thanks for joining me. We'll see you again next time here very shortly for part 2 of all this. Thanks.